Right.
Yeah. Hello, everyone. In the morning session, we had a discussion about the organic part, right? So, very good response was there from you. Fine. So keep going like that. So objective type questions and 4 answers with more answers. Always it is good to do that because out of 4, immediately we get the answers and immediately we get reinforcement. That's why MCQs are quite helpful. They are the building blocks of the total concept, right? So anything the if it is to be tested for the understanding level, it is objective type questions which are being asked. Therefore, CBSE has introduced this objective type question, and also it helps for the competitive examinations. Hope you were doing, and those who have not participated, try to participate in the coming session, right? So this is the academic support class from NVS RO, Hyderabad region. And I'm GR Maskeri presenting before you. And now we will go for physical chemistry chapter, right? Physical chemistry chapters. There are 3 physical chemistry chapters, which is to be taken. Okay, right? Okay. So this is chapter solution, right? First chapter solution, and based on that, what are the questions which are coming and which are the important concepts? Let us know about it, right? Okay. Solution. What is solution? Solution, you know that it is a homogeneous mixture of 2 or more substances. Homogeneity. What is meant by homogeneity? Homogeneity means in the microscopic level. Example is if the metals, however finely you powder and mix it up, it cannot be a solution because the finest particle also has got microscopic level, they are not uniform. Therefore, a solution homogeneous, the extent of microscopic level we take is 10 to the power minus 9 nanometer scale, right? So a brass is a mixture of copper and zinc, right? Brass is a mixture of copper and zinc. So this alloy is being prepared. Alloys are prepared by mixing the metals in the liquid state. When they mix it in the liquid state, it becomes a uniform or solution, right? So brass, bronze, right? Or German silver, these are all alloys and they are the homogeneous solutions, right? So there are many homogeneous solutions we will see in our day-to-day life, like perfumes, antiperspirants. Air is a homogeneous mixture, right? And steel is a homogeneous mixture, right? Brass and bronze, all this. Now, how this solution is formed, formation of a solution, right? So you are adding a solute and there is a solvent. Solute and solvent go into one another, right? If the 2 components, okay, they go into one another, right? And such a way that they becomes uniform to the microscopic level, as I said. If there are 2 components, only 2 components, then it is called as a binary solution. That means one solute and one solvent, that is called binary solution, right? Similarly, there is ternary and multinary solutions also. More and more components also can be there. The scope of the book is for binary solutions, right? So how it is undergoing uniformly, how it undergoes, let us see through this video. Okay, can't play this media. Okay, right. Solute molecules get attracted by the solvent molecules, right? And when each particle of a solute is surrounded by the solvent molecules, then we find homogeneous mixture like this. Solute particles are there here, and they get separated. They carry solvent molecules, carry all those them. They get separated. Solute particles get separated. That's what, when the salt is added to water, the salt is not being found at all when it is being dissolved, right? Each solute particle, that is salt, is being carried out, being carried by or surrounded by solvent molecules. This is what happens when the solution is being formed, right? Now let us see the energy conditions in this formation of solute. Thermodynamics is a part which tells about the energy conditions, right? Solvent particles are together and they have to get separated. Solvent attraction is to be separated. Solvent particles should come out of that. Solute particles again come out of their attraction. So for every process, there need energy. This is delta H1, enthalpy of this is enthalpy or the change in heat or energy required for making this solvent to be get separated. Solute to be get separated, delta H2. Then these two will intermix and the new attraction sets in. Whenever there is an attraction, there will be fall of energy, potential energy. Therefore, the energy required, the formation is delta H3. So here it is delta H3, say. So delta H of solution, that is enthalpy change in solution, is delta H1 plus delta H2 plus delta H3. All these enthalpy change in each process is to be added so that we get enthalpy of solution. What is enthalpy of solution? When 1 mole of solute is dissolved in 1 mole of solute is in specific solvent, okay, in specific solvent, right? Specific quantity of the solvent, then the energy released or energy absorbed or enthalpy change or heat change is called enthalpy of solution. Enthalpy of solution. Okay, it is required 3 form of energies. Solute should get separated, solvent gets separated, and solvent get attracted, right? Now delta H of solution, is it always positive or is it always negative? It depends. So for separation, always we need energy. Therefore that means delta H1 is positive. And for separation of solute particles, again, energy is to be invested. Therefore, this is also require energy. Therefore, delta H2 value is positive. But the new attraction, delta H3 is negative. Delta H3 is negative. So if the process results in process of solution dissolution such a way that delta H3 is more negative, then delta H of the solution is negative because it is sum of all this ring. Then delta H3 is negative. So delta H of solution may be positive or negative, right? Or it can be 0 also. Enthalpy change can be 0 also, right? So let us see more about this thing also, right? So delta H of solution is delta H1, delta H2, delta H3, right? So formation of solution. How exactly this happens?
That is present in a smaller quantity is known as the solute or the dissolved substance.
Okay.
The component that is present in a larger quantity is known as the solvent or the dissolving substance.
So when it is present in larger quantity is solvent, and when it is less quantity is solute. This is how the components are defined.
Solute in a solvent is called a binary solution.
Okay, so this is a binary solution. Binary solution, there are only 2 components, solute and solvent, right? Now, what are the types of solution? types of solutions are the solid solutions, liquid solutions, and gaseous solution, right? Solid solutions, we mean solid is the solvent. In solid, something else, small quantity that dissolves, right? Liquid solution means in liquid, another small quantity of solute dissolves. So that is liquid solution. Gaseous solution, in the same way, gases are present as solvents, right? So let us quickly look into the examples of it, right? Gas in gas, air is an example of gaseous solution. Okay, gas is a solvent. Gas in liquid, a gas can be in liquid, that is aerated drinks, carbon dioxide and water, whatever that we drink, Coca-Cola, Mazda, or whatever that carbonated drinks are there, carbon dioxide is dissolved in it, that is this one. Gas in liquid, gas can be there in liquid, hydrogen can be there in, gas can be there in solid, hydrogen in palladium. Hydrogen in palladium is an example for that. Hydrogen in palladium. Okay, hydrogen has got the palladium has got greater affection with hydrogen, so it dissolves, or it can be an interstitial, because palladium is having such a large voids in which hydrogen, a small atom, can be present there. So interstitial, it is an interstitial compound also. Liquid in liquid, alcohol in water, benzene in toluene, all these are liquid in liquids. So many examples are available. Liquid present in solid, okay. Mercury in zinc amalgam, mercury in zinc, that is called amalgam. Mercury is a liquid, so mercury and zinc, right, can be given example. Liquid in gas, carbon dioxide dissolved in water, liquid in gas, okay, right. And solid in liquid, sugar in water and common salt in water, much examples are available. Solid in gas is smoke particle, or smoke particle, and solid in solid is various alloys. So these are the examples of different solutions, right? So how now the task is how we have to write the expressions, or how we have to know about the concentration of solution. The solute will be in specific quantity. If it is in specific quantity, then we can able to write it in mathematical terms, right? The solute, okay, we can easily understand about it. A 10% solution is more concentrated than 5% solution, right? 10% solution contains 10 grams of solute in 90 grams of water. So this is percentage wise we express the concentration of that solution. 10% is more concentrated than 5% solution. 5% solution contains only 5 grams of solute in 95 grams of water. So total solution is 100 grams, in which how much solute is being present, that ratio is to be taken. So in this way, there are many ways of expressing the concentration, various ways. Let us look into this. So it can be qualitative or quantitative.
We describe the solution as either dilute or concentrated.
Okay, it is a rough way of saying dilute and concentrated.
The small proportion of solute relative to the solvent.
Solute is in a small quantity, right?
On the other hand, a
concentrated solution will be having more of the solute.
This qualitative means of describing concentration, although useful, sometimes leads to confusion, and thus arose the need for a quantitative description of solutions. Quantitatively, the concentration of a solution can be described in several ways.
Okay, so several ways it is expressed: mass percentage, volume percentage, mass by volume, parts per million, moles fraction, molality. So these are the various ways of expressing the concentration. Let us look into the definition of this. Mass by mass percentage is mass of solute by mass of solution into 100. Okay, you know about it, right? Okay. Volume by volume percentage is volume of solute by volume of solution into 100. Always this is a fraction less than 1. Volume of solute by volume of solution, or volume of mass of solute by mass of solution. Always there is a fraction less than 1. We have to multiply 100 so that it will come in percentage. Right. Mole fraction of a compound is number of moles of that component divided by total number of moles of that, the total number of moles in the solution. Right. So as far the definition is concerned, I think you are perfect, or you may know about it. So we'll quickly look into the other things. How the questions will come also we'll see. Molarity, number of moles of solute by volume of solution in liter. Volume of solution in liters. Okay. So this is molarity. Molality is number of moles of solute by mass of solution in kg. Now, which out of this is temperature dependent? Which changes, which concentration changes with temperature? Yes, good afternoon. Somebody has put the message. Guntur, Pondicherry, all right. So, which is temperature dependent? Can you able to tell? Just want to. Okay. This is the problem with. Okay. I was just seeing at the. Yeah. Yeah. This is mass of solvent in kg. Solvent, another important thing to this solvent. So volume is temperature dependent. If volume changes with temperature, therefore volume is temperature dependent. Therefore molarity is temperature dependent. Molarity is expressed in capital M. This is small m. Okay, this is moles per liter. This is moles per kg. Right? These are the units to be remembered. Molarity, molality. These are important ones. Now, if suppose the question is 4 grams of NaOH dissolved in 36 grams of H2O, calculate the mole fraction of each component in the solution. Also determine the molarity of the solution. Specific gravity is being given. So it is all numerical based. These are numerical based chapters, and questions can be asked in this way. 4 grams of NaOH dissolved in 36 grams of water. Calculate the mole fraction. How to get the mole fraction? Mole fraction. Now, application. You have learned the formula. Now, how to apply this? How to apply this? Right. Mole fraction is number of moles of solute. Mole fraction of each component it is being taken. So mole fraction of NaOH if you want. So the number of moles of NaOH to be written. Number of moles of NaOH. Number of moles of NaOH is given mass. Given mass is 4 grams divided by molar mass. Molar mass of NaOH is 40 gram per mole. 40 NaOH. Okay. So NaOH. Sodium is 23, oxygen is 16, and hydrogen is 1. Totally it is 40, right? Given mass 4 gram, not 49, 4 grams by 4 gram by 40. This is number of moles of it. So number of moles of sodium hydroxide and number of moles of water. Water also given in grams. So 36 is the given mass by molar mass. Molar mass is 18. Okay. So this is the one that you have to solve, so that we get mole fraction of sodium hydroxide. If it is a binary solution and mole fraction of one component is known, how will you find out the mole fraction of the other? Just by subtracting this by 1, right? Because if XA is the mole fraction of one component and XB is the mole fraction of another component, sum of this will be 1 for a binary solution. If you know 1, you get the value of the other by subtracting it by 1. Therefore, this is a mole fraction we can relate, right? So mole fraction of NaOH, you can do this. 4 by 40 is 0.1 and 4 by 40, that is 0.1, divided by 36 by 18 is 2, that is 2.1. 0.1 by 2.1 is 0.047, right? 0.047 is the answer. Okay. Okay, this is how you have got it, right? Okay, visibility, no problem. Now, calculate the molarity of 2% glucose solution. So, molarity of 2% glucose solution. What do you mean by 2% solution? See, you are expected to know about the mass by mass percentage, and then you have to, you should know the molality also. So, in this way, one question which makes you to know or makes you to test the knowledge of both the things. So this kind of questions are asked. So you should know about the molality and percentage. 2% solution means 2 gram of solute. 2 gram of solute in 98 gram of solvent. In 98 gram of solvent, right? This is what the meaning is. So given mass, we can take it as 2 gram, right? So what is molarity? Small m. Molarity is number of moles. So 2 divided by number of moles. It is glucose. Glucose is C6H12O6. Okay, sometimes they may not give the molar mass of the compound, right? So you may have to calculate, right? 2 divided by, this may be 180. Let us check that. Divided by 2% solution, 98 gram of solvent or 100 gram of solution, 100 gram of solution. What we need here is 98 gram. This is dissolved in 98 gram. We have to express 98 gram in kg. Therefore, you have to have a multiplication factor of 1000 here. Or you have to divide 98 by 1000 so that it will be coming in kg. Right? So this is what the thing that you have to calculate. This is what is required. Right? So 2 by 180. 180 is molar mass divided by 98 into 1000. Okay? Into 1000. Right. Okay. Right. So this is the way we get the answer, right? Sometime you may also, I ask you to do yourself also. I will wait for it. Better to have a rough paper with you, and how quickly you can come into the conclusion, or how quickly you can able to assess that what are the required information given, and what is the formula to be used. If you test yourself, or if you can recall yourself about this issue, then this will be of more use. Calculate the mass percentage of benzene and carbon tetrachloride if 22 gram of benzene is dissolved in 122 grams of carbon tetrachloride. It is NCERT question. It is in-text question of NCERT textbook, right? So in-text questions and NCERT questions, solved questions, always look into that. It's important, right? So calculate the mass percentage of benzene, mass percentage. If 22 gram of benzene, mass percentage is m by m percentage. Mass percentage is mass of solute by mass of solvent into 100, right? Calculate mass percentage of benzene that is carbon in tetrachloride. If 22 grams of benzene is dissolved in 122 grams, right, into the 100. It's a direct question. Direct mass by mass percentage is mass of solute by mass of solution into 100, right? Okay. So this is how mass percentage of benzene C6H6 is mass of C6H6 divided by total mass of solution into 100. Okay. So that you will get 15.28%. 15.28% is the answer, right? And mass percentage of carbon tetrachloride, when you want to find out, 100 minus 15.28 you can do. Therefore, it is 84.72. Okay. So in text question, another one. Calculate the mole fraction of benzene solution containing 30% by mass in carbon tetrachloride. 30% by, we have to find out the mole fraction. Take your paper and see what are the things given and what do you comprehend, what do you understand. I'll wait for 1 minute. Calculate the mole fraction of benzene. Mole fraction of benzene. Benzene is equal to dash by dash. This is number of moles of benzene C6H6. I write like this. Number of moles of C6H6 plus the solvent. Which is the solvent? Mole fraction of benzene in, okay, calculate the mole fraction of benzene in solution containing 30% by mass solution of carbon tetrachloride. So number of moles of carbon tetrachloride, CCl4. This is the formula of it. Mole fraction of the benzene. So it is 30% by mass. Again, you should know about the number of moles of each one by this. 30% by mass means what? 30% of the solution we mean 30 gram of solute in 100 gram of solvent, right? 100 gram of solvent. So 30 gram of solute, 30 solute is here benzene. So mole, how will you convert number of moles of benzene? 30 divided by molar mass of it. So you need number of, okay, so total mass of solution is 100 and the mass of benzene is 30. Total mass of carbon tetrachloride is 70. This also we'll understand. And molar mass of benzene, we have to calculate C6H6. 12 into 6 into 1 into 6, that is 78. 78 is molar mass of it. Number of moles of benzene is therefore given mass by molar mass. Given mass by molar mass. 30 by 78, that is coming to be 0.3846. Points. Okay, once the logic of doing it is understood, rest of the things are not that important. It will go on its own, right? So the basic mathematics, right? Now, molar mass of carbon tetrachloride also is to be found out. It is 154. Carbon tetrachloride, right? Okay, internet connection is unstable. Anything? Can you able to see those who are in Zoom meet? Some internet issues are there. Hello? Okay. So mole fraction of benzene in carbon tetrachloride is number of moles of benzene by number of moles of benzene plus number of moles of carbon tetrachloride. Therefore, this whatever that it is already found out, number of moles, it is being substituted and answer is being found out. Okay. So what is very important? Have the you should have the correct formula. So this formula you have to recall. Meeting in now streaming live on custom live streaming service. Okay. I think there is some issue with internet. Now, calculate molarity of the resulting solution if 30 ml of 0.5 m H2SO4 is diluted to 500 ml. Yes, this is also interesting question. So you have got only 30 ml. Only 30 ml of this 30 ml of 0.5 m H2SO4. This H2SO4 is 0.5 m, half molarity, 0.5. If water is being added up to, and this is 500 ml now, diluted. Now find out the molarity of the resulting solution. When 30 ml is diluted, now you have to find out molarity of the resulting solution. So what you have to find out is 30 ml of 0.5 ml solution is taken. How many moles of H2SO4 is taken there? Because number of moles of H2SO4 doesn't change when water is being added. Okay. Number of moles of H2SO4 doesn't change if the water is being added. Number of moles, I tell you. Now, how to calculate? What is meant by 0.5 m? 0.5 m H2SO4 means 0.5 moles of H2SO4 in 1 liter of solution. 0.5 m H2SO4 in 1000. 1 liter means 1000 ml of solution. This is what we have the information. In 1000 ml, 0.5 moles are there. Therefore, for 30 ml, how much moles are there? You have taken. Because initially, only 30 ml of 0.5 m H2SO4 is taken. Therefore, 0.5 m H2SO4 means 0.5 moles present in 1 liter of solution or 1000 ml of solution. But 1 liter you have not taken. We have taken only 30. So, only a part of or some moles of that only will come in that. Therefore, number of moles of H2SO4 in 1000 ml is 0.5 solution is 0.5 moles. Therefore, number of moles of H2SO4 in 30 ml. So this is 0.5 into 30 divided by 1000. Therefore, it is 0.015 moles, right? So now it is diluted to 500 ml. So solution is 500 ml. Okay, whatever amount of water is added so that it becomes 500 ml, so that 500 ml solution. Therefore, now we have to find out the molarity. Molarity is the number of moles, right? Number of moles of it divided by volume of solution in liter. That is, volume of solution is 0.5 is written. Volume of solution, because 500 ml is 0.5 liters. Okay. So this is 0.03 m. Okay, it is also a textbook question. Therefore, it is also important. Now, the same question can be done in another way also. There is another formula called M1V1 is equal to M2V2. This formula, we can use it for dilution of a solution. If M1 molarity of a solution, if you have taken V1 ml of it, and then we have changed it into V2 volume, then what will be the molarity of it? Okay. So if this case, if you take, we have taken the question is, I'll go back. We have taken 30 ml of 0.5 m, 30 ml of 0.5 m, right? We have taken 30 ml. Okay, this is an ml, 30 ml of 0.5 m solution. M1 is 0.5 m, V is 30 ml. Now this is equal to, we have to find out the new polarity, and volume of this has become 500 ml. 500 ml, because volume V2 is 500 ml, diluted to 500 ml. Now M2 can be calculated by 0.5 into 30 divided by 500. This calculation will help you. Okay. So this also will become 0.03. You can check 0.03. Okay. 0.5 here. Okay. This is 1. If you take it as this is 0.5, then 3 into 10 to the power minus 2, that is 0.03. If you do this calculation, you will get the same answer. So this is easy to do this if you know the formula. So on dilution from volume V1 to V2, equation that can be used is M1 V1 is equal to M2 V2, right? Or else, if one solution is mixed with another solution having different molarities, then how to find out the molarity of the resulting solution? For that also there is a formula. On mixing two non-reacting solutions, final molarity of the solution can be given by M1 V1 plus M2 V2. These are the two solutions which are being mixed. Okay, gives M3 V1 plus V2. Volume of the solution, resulting solution will be V1 plus V2, right? Therefore, this is the formula that can be used. We will apply this also. Objective type questions, such questions will come. Right. Now, look into the question and try to apply this. 2.5 liters of 1M H2S, 1M NaOH solution is mixed with another 3 liters of another 0.5M NaOH solution. Both are NaOH solution, right? Then find out the molarity of the resultant solution. You tell me what is the calculation to be done. You need not tell the answer. If the Zoom is intact, you can tell. Okay, Guntur Yanam. Okay. So okay, I have just taken that. Right. Right. So this is the answer. But how you have found out this, right? Okay. I think this has also. Okay. Right. Just a minute. Right. So 2.5 liters of 1M NaOH. So M1 V1, the same formula that we have to use, is equal to M2 V2. Look at this. 2.5 liters. It is in liters. And 1M solution, 1M, 1 into 2.5 is equal to 0.5M mixed with another, sorry, this is not dilution. 2.5 liters of 1M NaOH solution is mixed with, okay, is mixed with, okay, is mixed with, right, M3 V1 plus V2. So this is 2.5 into 1 plus M2 0.5M into 3 liters So resulting solution is M3 you have to find out. M3 you have to find out. V1 plus V2. V1 is 2.5 and 3 liters, that is 5.5. Okay. Now M3 is equal to simple one, 2.5, simple calculation only. This is 1.5, that is 4. 4 divided by 5.5. Okay. So this is come to be 0.73. Okay, you can see, check the answer, 0.73. Mole fraction of a solute in 1 molar aqueous solution is, mole fraction of a solute, mole fraction of a solute in 1 molar aqueous solution is, one molar aqueous solution. 1 molar means what? 1 small m solution. 1 m solution means what? 1 mole of solute, 1 mole of solute in 1 kg of solvent. Right. 1 kg of solvent. Right. 1 mole of solute. You have to express the mole fraction. 1 mole of solute, mole fraction is number of moles divided by total number of moles. So this is 1 kg. Aqueous solution means 1000 grams divided by given mass. 1 kg means 1000 grams, 1 kg of solvent divided by molar mass of it, 18. This is 15.5, 55.5. This value is 55.5. Therefore, 1 divided by 56.5. This value you have to find out. 1 divided by 1 plus 55.5. So that you get the answer to this. So this answer will be 0.0177. You can verify. Now, so NCERT text questions always are important. So I ask you to look into that. We have solved few questions, and the few questions which are very important is calculate the molarity, molality, and mole fraction of Ki. It is an in-text question only. Okay, and calculate this and see. Okay. Now let us move on to another concept. So methods of expressing concentration is one concept on which the questions are asked. Second concept is solubility and the factors that affect solubility. What is meant by solubility of a solute? Solubility of a solute is the maximum amount of solute. It is the maximum amount of solute that can be dissolved in a specific amount of solvent to form a saturated solution of it at that temperature. Saturated solution. If you want, suppose 100 gram of water you take, go on adding the sugar until the sugar cannot be dissolved further. That is saturated solution. So you go on adding, and while adding, go on add with the calculated amount, the amount that you have added, so that it has become saturated. That is the solubility. So the same water, 100 gram of water, if you, the solubility of sugar and solubility of sodium chloride, are they same at the same temperature? It is not so. It depends upon nature of solute. Therefore, solubility depends upon the nature of solute. The extent to which it dissolves are different. Therefore, solubility of sugar and salt different. Solubility of common salt at 30 degrees Celsius, is 36.09 per 100 gram per 100 ml. So what do you mean by this? If you take 100 ml of water and go on dissolving the common salt, it requires that 36 up to 36.09 grams it dissolves. Afterwards, whatever the amount you are added, it will remain there undissolved and present as a salt, present as a solid material in at the beneath of the solution. So therefore, this is solubility, and the temperature is necessary to be mentioned. Solubility may change with the temperature, right? How it changes, we'll look into that. Now, amount of solute needed for the saturation is called solubility, right? So this is unsaturated solutions contain the solute less than the saturated solutions. All that solutions which contains less amount than the saturated solutions form unsaturated solutions. And for the unsaturated solutions, we express the methods of concentration. We have got different ways of expressing the concentration. Now, what are the factors that affect solubility? What are the factors that affect solubility? As it is definition is said, temperature affects the solubility, right? And nature of solute and solvent, both, right? As I told you, the solute, the sugar and the salt, it is different. Same, the nature of solute and solvent, temperature is another factor. Temperature is more, whether solubility increases, let us see that, how it exactly does for different solute, right? And pressure in case of gaseous solute, pressure in case of gaseous solute, right? What happens? Let us see. Nature of solute and solvent. So nature of solute and solvent is very important. Then only the dissolution takes place. So dissolution can be otherwise told like this. There is solute interaction, AA interaction. Between two particles of solute, there is always interaction, AA interaction. And between solvent, there is interaction, BB interaction. When these two are mixed, then this will be AB interaction. A particle of solute and particle of solvent get attracted, right? Interacted. So if AB interaction is same as AA and BB interaction, then dissolution happens. Dissolution will happen, right? Attraction between the solute and solvent is a very important thing here. Therefore, there is a word called, a sentence called like dissolves like. Like dissolves like. Water being polar, it dissolves all polar compounds and also ionic compounds. Ionic compounds are having +1 charges, charged species. So they get dissolved because of the polarity of the water. Each ion is surrounded by polar water. Therefore, ionic compounds almost all ionic compounds dissolve in water. So therefore, water is called as universal solvent. It dissolves many of the solute, right? So among the gases, increasing molecular mass or polarity increases solubility. Another thing that important is the gases, among the gases, increasing molecular mass or polarity increases the solubility. The gases which are having more polarity or more mass dissolves more. This is due to London's or dispersion forces. Dispersion forces. As dispersion force increases, van der Waals force of attraction increases as the size increases, right? So because of that, it is so. Substance with similar molecular interaction forces tend to be soluble in one another. I told you that like dissolves like. That is the one. Polar liquid tend to dissolve in polar solvent. As I told you, water is a polar, can form hydrogen bonds. Non-polar liquids tend to dissolve insoluble in polar liquids. That's how the matching or it doesn't match means it won't dissolve. Petrol is insoluble in water. Petrol is non-polar. Okay, but petrol dissolved in benzene, right? So petrol is soluble in benzene. Now, given a situation, can you able to let me just your understanding. Two solvents are being given. Hexane, one is hexane, another is methanol. Two solvents are given. And there are two, which of the better choice to act as a solvent for two solutes. These two are solutes. For this grease to be get dissolved, which is the best solvent among these two? Look at that. If you have understood the concept, you can able to tell this. Grease, the molecular formula also is given, C20H42, grease. It is a hydrocarbon. Hexane is a hydrocarbon. Non-polar, non-polar. Therefore, hexane dissolves better in, grease dissolves better in hexane. Potassium iodide, ionic compound. Methanol is having polarity, hydrogen bonding, right? Methanol is the better choice for this. So grease dissolves in hexane and potassium iodide in methanol is the better choice. Okay, dissolves. Now solubility versus temperature. Whether increase in temperature increase the solubility of all solutes. So you may guess like that, but it is not so. Solubility curves give the clear picture about it. Solubility curves. These are the solubility curves. So at temperature, when the temperature increasing temperature, the amount of solute necessary for making it a saturated solution is plotted here. So you can see here the NaCl almost a flat kind of, okay, slightly increases, slight increases, that's smaller slope. Okay, so here it is KCl. This is NaCl and the blue one is KCl. Potassium nitro3 steep curve. Lead nitrate, calcium chloride, NaNO3. They are all increasing with increase in temperature. Increase with increase in temperature. But one which you can find, which has got downtrend curve, cesium sulfate, right? So the solubility curve gives you the clear picture about how temperature changes the solubility of that particular solute. Now it need not be all solute, okay, all solute, main solubility of which may increase with temperatures, may not be so. It may not be so. Okay. So what about NaCl? By increasing of 10 degrees Celsius also, the increase of solubility will be very, very less. But in case of KNO3, okay, with the 10 degrees Celsius change, the solubility changes a lot. Okay. So this is how we can able to understand from the graph. And why it is so? It goes with delta H solution values. Okay. For those delta H value is negative. Negative in the sense heat is evolved in the process. It is an exothermic process. Say exothermic, this is negative. For these those who are negative, delta H is negative. That is the exothermic process. Heating the temperature won't or giving more temperature or heating won't increase the solubility. So this cesium sulfate dissolution is a exothermic process, therefore it decreases. For most of the solute, delta H solution is positive. If this is positive, then increase of temperature increases the solubility. If it goes on increasing temperature, it increases. Right. The steep curve indicates that it is highly endothermic. The process of dissolution is highly endothermic. So KNO3, probably if you do this experiment in the laboratory, take some potassium nitrate in the test tube, add little water, and hold the test tube in your hand like this. Hold the test tube. Okay, you will feel as if you are touching a ice. That much cold it is, right? It is endothermic process. Dissolution of KNO3 is endothermic process. You can see that. So this is how we understand how temperature changes. Okay. Okay. So as temperature increases, the solubility increases with few exceptions. Okay. Normally it increases with few exceptions. Cesium sulfate is an exception. Okay. For the solution of gases, what do you say? For the solution of gases. For the solution of gases, if oxygen is to be dissolved in water, increase if you take the boiled water and do you expect oxygen to be dissolved there? No. So as increasing of temperature, the gases solubility decreases. Okay. Solubility of the gas decreases. Okay. So with increase in temperature. That's why in the summer season, in ponds where there is little water will be there, the fishes die because insufficient oxygen will be available for the aquatic life. The dissolution of the oxygen becomes less at higher temperature in the summer, and because of which aquatic life is affected. Now, how pressure affects. So there is a gas here, and you are increasing the pressure. By increasing the pressure, the gas over the liquid, more of the gas will be there inside the liquid. Okay. So application of pressure increases the solubility of the gas. Okay. Application of pressure increases the solubility of the gas. Right. There is a rule, there is a law called Henry's law. Henry's law gives the mathematical expression for that. Okay, due to the increase in the gas. So, okay, what is Henry's law? Henry's law is the solubility increases, or the dilubility of the solubility of the gas increases in direct proportion to its partial pressure above the solution. Okay, so mathematically this can be written in this way: partial pressure of A. So here, understand it. Here is a liquid. There is a liquid, and the gas above it. This is the gas, and you are applying pressure. As the pressure increases, this mole fraction of this particular gas inside the liquid increases. So PA is directly proportional to XA, mole fraction of A, and KH is called Henry's constant, right? Henry's constant. Okay, so you can have the graph, look into the graph also. Mole fraction of HCl in the solution of cyclohexane increases by applying the pressure. As pressure increases, it is a linear curve. Okay, and it starts with 0, right? Slope is 0. This intercept is 0 for that. Plus C is 0, right? Now, application of Henry's law. Henry's law will suggest about how the pressure affect the increase in solubility. We are also breathing. Our breathing is according to the Henry's law. I mean, more and more is get dissolved if the pressure of the oxygen is more, right? In the bronchus, oxygen get dissolved because of the pressure of oxygen. Oxygen dissolved into the blood at the lungs because of the pressure of the oxygen in the air higher, okay, allowing it to dissolve in the bloodstream. Okay, this is the reason, and this tells you about this is actually the direct impact of the Henry's law. Okay, of course, this is how he explained the concept of this kind. And there is another psychological state, or the physical state that obtained when we move into the mountains, right? So the mountaineers at higher altitude will have less oxygen. If they carry oxygen cylinder, well and good. But those who are staying in the mountains, they get less amount of oxygen in the bronchus. Can you tell me why? Because at the higher altitude, the partial pressure of the oxygen is less. Oxygen less will less get dissolved. Because of this, people will be inefficient in thinking. People will be inefficient in thinking because of less amount of oxygen that get dissolved there. Low oxygen supply in the tissues, it gets weakness and inability to think clearly. Okay, this is called anoxia. Okay, it is called anoxia, right? So only the pranayamas or breathing techniques makes more and more oxygen to be get dissolved, and so that person will become healthy, and also tissues will be getting the oxygen, and also he can think properly. right? There is another concept called bends. What is this bend? You may be knowing about the deep sea divers, those who work under the beneath of the sea. So they carry a cylinder, okay, which contains oxygen gas along with the nitrogen gas also. Because in day-to-day life, in the atmospheric air, oxygen and nitrogen, both gases are there, and we are habituated to inhale the nitrogen also along with oxygen, and we exhale the nitrogen back. But the same mixture is being carried out in the breathing mixture that is being carried out by them earlier. And what used to happen is nitrogen, when nitrogen present in the breathing mixture, get dissolved in the bloodstream because of the high pressure. At the beneath of the sea, there will be high pressure. And therefore, nitrogen get dissolved in it. While dissolving, there is no problem in it. But when a person comes back to the surface of the sea, the extra nitrogen dissolved will come back in the form of bubbles. So that gives extreme pain, and because of which he gets bends. This pain or the condition, physical condition, is called bends, right? So what is the solution? The solution is the one which carried as a breathing mixture nowadays, that contain the less soluble helium gas also. Okay, so the nitrogen, if it get dissolves, then helium is better alternative. Its solubility is less. Okay, so knowing about the solubility and the changes that is made, all these are the applications of Henry's law, right? Okay, and another thing is that bottling the carbon dioxide. Okay, if this 7 grams or 8 grams of carbon dioxide is to be dissolved in a particular amount of solvent water at this temperature, okay, so how much should be the pressure applied? Okay, so this kind of mathematical solution can be got by Henry's law, right? So bottles sealed under high pressure, okay, bottles sealed under high pressure, and Henry's law is the solution for all that, how much pressure is to be applied and all that. We are going to solve some questions based on that also, right? Okay, so solubility of CO2 in soft drinks and soda water, this is being calculated by looking by the mathematical expressions of Henry's law. So these are the applications of Henry's law, right? Now there is a Raoult's law. Raoult's law is something about vapor pressure. Vapor pressure. So you know that every liquid has vapors. The liquid converts itself into gaseous form. This is the escaping tendency of all liquids. The liquids on the surface escape because of the residual forces. Now the vapors apply pressure. Vapor gives pressure. Suppose if in an evacuated vessel, you are having a pressure measuring device, manometer, right? Pressure measuring device, and you have taken a liquid here. This liquid gets into vapor at that temperature. It converts into vapor, right? And after some time, there may be a condensation also. When the vapors get increased, okay, they get condensed. When these two opposing forces are equal, then that sets in equilibrium. When when the vapor is in equilibrium with liquid, the pressure applied by the vapors is called as vapor pressure of the liquid. Okay, so it is at a given temperature, for a solution of volatile liquids, the partial vapor pressure of each component is equal to the product of the vapor pressure of the pure component and its mole fraction. This is Raoult's law. Suppose if you have taken pure water here, pure water, so this is denoted as P0. P0. Suppose the component, this is water, I will call it as A, P0A. P0A is pure solvent or pure liquid, say. So if you make a solution, you have dissolved some sodium chloride in it. So when you add sodium chloride, being a non-volatile sodium chloride solute, it decreases the vapor pressure of this. It decreases the vapor pressure of pure solvent, right? So the decrease or the vapor pressure of the solution, if it is represented as PS, this is equal to vapor pressure of the pure component A into mole fraction of A. Okay, mole fraction of A, P0A into X mole fraction of A will be the pressure of the solution. Now pressure of the solution is nothing but P of A only, because only water is present to give the vapor. PA is equal to P0A into XA is the mathematical expression of Raoult's law. What it says, that look into that. At a given temperature, for a solution of volatile liquid, the partial vapor pressure of each component is equal to partial vapor pressure of each component is equal to the product of vapor pressure of the pure component and its mole fraction XA. PA is equal to P0A into XA. Okay, so this is how you can apply that. If both are liquids, if both components are liquid, then both will form the vapors. Then the vapor pressure of the solution is due to both the vapors of both the components. Therefore, we can write P total vapor pressure of the solution is PA plus PB, or PA is given by P0 A into mole fraction of A plus P0 B into mole fraction of B. Right. Therefore, this is the expression that can be used for solution having both volatile components. And this is the formula that you can use it for vapor pressure of one of the component. Only one volatile component is there, then you can apply this particular mathematical formula. Okay, so PA is equal to P0 A by B0 A into XA. That's what the mathematical expression is. Okay, fine. So this is what I told you about it. Now, solids in liquid solution. Solids in liquid solution, but is solid which is non-volatile, say. Solid is non-volatile. Then we can draw mole fraction versus vapor pressure. Mole fraction varies from 0 to 1. In a solution, the two components are there. One is solute, another is solvent. If solute quantity goes on increasing, mole fraction decreases. This is vapor pressure of the solution decreases. Mole fraction of solvent, that is giving weight, increases. Mole fraction of the solvent increases, vapor pressure increases. Vapor pressure also increases. Therefore, this is the curve for vapor pressure, mole fraction of solvent to be remembered. Okay, increase of non-volatile solute, the vapor pressure of the solution is lower than that of the pure solvent, right? So pure solvent, and when the solute is being added, the number of particles are getting reduced, you can say, and vapor pressure also decreases. Vapor pressure decreases. When solute concentration goes on increasing, vapor pressure decreases. When pure solvent increases, vapor pressure increases. Okay, this picture will be easy to make you to remember it easily. Okay, right. So these are the expressions for the solutions in which both the solute are volatile. Okay. Now, coming to the graph of such kind of solution. So both the graphs, this one and this one, both can be depicted in one graphical page. The mole fraction of the solvent, one solvent or one component, is from 0 to 1. 0 to 1. So mole fraction of the solvent increases like this. As that particular solvent, mole fraction increases. It is 0 to 1. If one component is increased, another component automatically decreases. Okay. Therefore, Xi2 or X2 ranges from 0 to 1 here. Okay, here given is 0 to 1, X2, therefore it is X2. Yeah, this is X1 and this is P1. And if you can draw a line here, this is the vapor pressure of the solution at a particular composition, at any composition. At any composition, this is the vapor pressure of the solution. This is what we can understand from the graphics. Now, what is the P0, P01? The one component, P01. This if it is pure. So if X1 is 1, then if X1 is 1, mole fraction of that one is 1 means other component is not there. Mole fraction, that component is 1, only that component is there, therefore the pure component. So the vapor pressure is here, that is vapor pressure. Therefore, this graph beautifully depicts the condition of the two components which are forming solution. Right. Okay, check your understanding. The vapor pressure of pure water at 110 degrees Celsius is 1.40 atmosphere. The solution of ethylene glycol and water has a vapor pressure of 1 atmosphere at 110 degrees Celsius. Assuming that Raoult's law is obeyed, what is the mole fraction of ethylene glycol in solution? Okay. Vapor pressure of pure water and ethylene glycol, both are volatile, right? The vapor pressure of pure water is 1.4, therefore P0 of water, okay, P0 of water is 1.4 atmosphere. This is being given. A solution of ethylene glycol and water has a vapor pressure of 1 atmosphere. So P total is being given. A solution has this vapor pressure. Okay. A solution of ethylene glycol and water has the vapor pressure of 1 atmosphere at the same temperature, 110 degrees Celsius. Assuming that Raoult's law is obeyed, what is the mole fraction of ethylene glycol? What is the mole fraction of ethylene glycol is being asked. Now, we take up P0 H2O, okay, and okay, and the solution, okay, we can write the expression, the total expression, P total, we can give the expression for P total and we can do that. Look at this. X of H2O can be calculated, mole fraction of H2O can be calculated. So by using this is already given, right? Okay. So mole fraction of ethylene glycol is 1 minus this will give 1. Mole fraction of 1 is known, another can be found out. Okay. Okay, I think we have to water has vapor pressure, that is PA is equal to P0 A into XA. By using this particular expression we can able to have. So this is 1 atmosphere, right? And P0 A is 1.40 and you are asked to find out mole fraction. Therefore, XA is 1 divided by 1.4. 1 divided by 1.4, that is coming to be 0.714. And mole fraction of 1 is known, another can be found out easily. Okay, that is the one you can able to do. 1 minus that. Okay, fine. Now, the ideal solution, the solutions, or whether all the solutions formed are ideal. What is meant by ideal solution? The solutions made are called to be ideal if when mixing, after mixing the two components, there will be no change in the heat generated, or delta H after mixing is not changed. And suppose if you mix two components, suppose 10 ml of one component A and 10 ml of another component B, if you have mixed, the solution should be of 20 ml as naturally so, 20 ml. But if it is found to be 21 ml or 19 ml, then it is non-ideal. If it is exactly 20 ml, then it is ideal solution. So why it happens so? Let us explore that. So this is ideal solution. Ideal solution which obeys the Raoult's law. Those solutions which obey the Raoult's law are called ideal solutions. Over a range of concentration, all range of concentration, whatever the concentration, if obey the Raoult law, then it is ideal solution. Okay. Solution made by benzene and toluene. Benzene and toluene is an ideal solution. Okay. And in this, intermolecular attractive forces between AA and BB are same as AB. This is an ideal solution. As I told you, the conditions of solubility, the interaction between the solute and solute, AA interaction, interaction between the solvent and solvent, BB interaction, and interaction between solute and solvent, AB interaction. If all these interactions are same, then solutions are easily formed, right? So then there is a condition for creating ideal solution. Now, which are the characteristics of ideal solution? So if the Raoult's law is obeyed, this graph is also obeyed. This is from Raoult's law, right? So if this is obeyed, if this is obeyed, this is so. If PA is equal to P naught A XA, if it is not more than or not less than, okay, if it is equal, then Raoult's law is obeyed. And delta H mix is equal to 0. That's what I told you. When you mix the two components, there is absolutely no change in the temperature. Heat energy is not evolved or absorbed. Then delta H mix is 0, right? Delta V mix, volume also is not changed. Benzene and toluene is an example of ideal solution, right? Now coming to the non-ideal solutions. So solutions which do not obey the Raoult's law are non-ideal solutions. And causes of these deviations lie in the nature of interactions at the molecular level. Molecular level, how the interaction is different, that we have to understand. Then it becomes a non-ideal. Whenever the non-ideal, the delta H mix for them is maybe positive or negative. Delta H mix may be positive or negative, or delta V mix may be positive or negative. Suppose if, okay, non-ideal solutions are there, they may show positive deviation or negative deviation. There are two non-ideal solutions. Non-ideal solutions with positive deviation and non-ideal solutions with negative deviation. Let us see the positive deviation. What do you mean by positive deviation? Okay, so this green one is supposed to be followed by the components, but they won't follow that. They are more than what you expected. Vapor pressure is more than what you expected. Therefore, when you form a solution also, the noted vapor pressure is more than what is expected from the Raoult's law. So vapor pressure of the solution is more than what you expected from the Raoult's law, then it is showing positive deviation. What are the other characteristics of positive deviation? So PA, partial pressure of A, is more than product of P naught A in mole fraction of A. This is always more than. Delta H mix is more than 0 and delta V mix is more than 0. These are the conditions for. Positive, easy to remember. If it is a positive deviation, delta H mix is also more than 0. Delta V mix also is more than 0. Okay, so this is a positive deviation. That is what going to happen. Okay, example, cyclohexane and ethanol. Cyclohexane and ethanol show this positive deviation, right? Vapor pressure will be more than expected because ethanol and cyclohexane. Ethanol is having hydrogen bonding. When cyclohexane is added, its interaction hydrogen bonding is broken, right? Because cyclohexane comes in between. Therefore, the interaction decreases. AB interaction is less than AA and BB interaction. Okay, so it is being written there. Right, interaction is less. When the interaction is less, volume increases. Interaction is less, they get separated a bit. Volume increases. Therefore, delta V mix is greater than 0. Volume increases, therefore delta V mix is greater than 0. This is what happened. So negative deviation. So this is expected from the Raoult's law, but it is less than what is being expected. That is kind of vapor pressure. That is the vapor pressure curve we get. So show negative deviation. Okay. Attractive forces between AA and BB is weaker than AB, leads to decrease in vapor pressure. Right. So negative deviation, PA will be less than product of this, PB also less than P naught B into XB. Delta H mix also is negative, delta V mix also negative. Delta H mix is negative means what? Heat is evolved in the process. Heat is evolved in the process. A more interaction after AB interaction is more than AA and BB interaction. Therefore, it is negative deviation. And sign of delta H and delta V also negative. So easy to remember in that way. Okay. Okay, fine. So chloroform and acetone, right? Chloroform and acetone. This is just to compare. Positive deviation above, negative deviation below the expected curve. These are the two graphs that you're supposed to remember. Now, for those which are having positive deviation, in a positive deviation, there will be a peak, peak point. Okay. And this composition, a particular composition, for a particular composition of A and B, maybe in 2:3 ratio or 1:5 ratio, whatever may be there, that particular composition, the vapor pressure is maximum. Vapor pressure is maximum. What happens when the vapor pressure is maximum? Boiling point decreases. Okay. So, such a mixture, this is a mixture of this composition. At this composition, the mixture behaves like a pure liquid. How? If you do want to separate them by fractional distillation, this is not possible. Such a composition is called azeotropic mixture, right? Azeotropic mixture. So binary mixtures having the same composition in the liquid and vapor phase and boils at a constant temperature, in such cases, it is not possible to separate the components by fractional distillation. This is called azeotropes. Okay. So there are two types of azeotropic mixture. One is minimum boiling azeotrope. Minimum boiling azeotrope is ethanol and water. So which shows positive deviation. Okay, vapor pressure is more. When the vapor pressure is more, boiling point is less. Therefore, minimum boiling azeotrope. 95% alcohol. You can separate alcohol. Okay, whenever alcohol is synthesized, and if you increase the percentage of that, fractional distillation we do, up to 95% we can do. But after 95%, okay, so if you distill it, again 95% alcohol only will be obtained. Therefore, this behaves like a pure liquid, 95% alcohol. And the maximum boiling azeotrope, nitric acid and water, 68 and 32%. Okay, it is 68% of nitric acid solution behaves like maximum boiling azeotrope. So maximum boiling azeotrope always show negative deviation. Negative deviation. Okay. So these things to be remembered. Okay. Summary: what we have learned so far is solubility of gas in solution, right? Henry's law, vapor pressure of the solution, Raoult's law, ideal and non-ideal solution, and the graphical representation, and then azeotropes. Now, some questions that we can take for revision. Maximum amount of solid solute that can be dissolved in a specific amount of a given liquid solvent does not depend upon. Can you tell the answer on one out of the 4 answers? Come on. Maximum amount of solid solute that can be dissolved in a specific amount of given liquid solvent does not depend upon. Does it depend upon the temperature? Yes. Does it depend upon nature of solute? Yes. Nature of solvent also. Then pressure, is it so? Pressure also depends, no? You maybe get confused, but here is the key word to be known. Solid solute. If solid solute is there, pressure has no effect. Okay. So this is the question from exemplar book. Right? So questions are taken from exemplar book. On dissolving sugar in water at room temperature, solution feels cool to touch. Under which of the following cases dissolution of sugar will be most rapid? So one condition is being given. After dissolving, it is cool to touch. What do you mean by this? The process of dissolution is endothermic process. If it is endothermic process, heat is absorbed. Then it becomes cool. Right? So which condition favor the dissolution of sugar, or rapidly it can be? Sugar crystals in cold water, sugar crystals in hot water, powdered sugar in cold water, powdered sugar in hot water. So powdered sugar in hot water. Powdered sugar, more surface area, it can be get into separated very easily, therefore. And hot water, more the temperature, more will be the solubility. Because it is feel cool to touch, endothermic process. Those which are endothermic process, heating increases the solubility of it. Powdered sugar in hot water. Low concentration of oxygen in the blood and the tissues of people living in the high altitude is due to. Exemplar question. Low concentration of oxygen in the blood and the tissues of the people living at high altitude is due to low temperature, low atmospheric pressure, high atmospheric pressure, both low temperature and high atmospheric pressure. So you may feel like saying this is the answer, but it is not so. The answer is only low atmospheric pressure. Okay. Exemplar question. This is an exemplar question. So low atmospheric pressure, because of that, the blood and tissues the living in the high altitude are having less concentration of oxygen, Okay. It is not high atmospheric pressure, high atmospheric. Okay. So both low temperature and high atmospheric pressure. Okay. This is only atmospheric pressure. Which one of the, come on. Which one of the following is the non-ideal solution? Benzene plus toluene, N-hexane, N-heptane, ethyl bromide, ethyl iodide, CCl4, CHCl3. Non-ideal solution. Remember, these all the three are ideal solutions. Okay, benzene, toluene, N-hexane, N-heptane, ethyl bromide, ethyl iodide, bromobenzene, chlorobenzene. All these are ideal solutions. CCl4 and CHCl3, they are not ideal solutions. Okay, so this is the answer of this. Okay, Now, assertions and reasoning type, one you will see to end up with. Azeotropic mixtures are formed only by non-ideal solutions, and they may have boiling points either greater than both the components or less than both the components. Is it true? Azeotropic mixtures are formed only by non-ideal solutions. Yes, it is true. They are formed by only non-ideal solutions, and they may have boiling points either greater than both of the components or less than both of the components. Azeotropic, maximum boiling, minimum boiling. Therefore, it is also true. It's the right sentence. The composition of vapor phase is same as that of the liquid phase in an azeotropic mixture. The composition of the vapor phase is same as that of the liquid phase in the azeotropic mixture. This is also true. Both are true, but this is not the reason for why the boiling point is greater or less. Therefore, B is the answer to this. Okay, fine. These are the important questions of this area. We will see colligative properties and the numericals based on that in the next session that I'm going to take, right? Okay, there will be more numericals or important numericals for the examination are to be dealt in the next session. Thank you. Not coming.